Hi class, and welcome back, and today we're going to talk about section 5. Okay, so chapter 1 section 5, and we're going to talk about applications and modeling with quadratic equations now. Okay, just like we did with linear equations. So we're going to talk about geometry problems, we're going to talk about the Pythagorean theorem, and also finding the height of a projected object, okay, and also modeling with quadratic equations. So again, how do we model either data or some real situation going on? So let's talk about volume. So solving a problem that involves volume. Okay. A piece of machinery produces rectangular sheets of metal such that the length is 3 times the width. Okay. Equal-sized squares measuring 5 inches on a side can be cut from the corners so that the resulting piece of metal can be shaped into an open box by folding up the flaps. Okay, so you're cutting out a square corner, and then the resulting flaps on each side can be folded up to create an open box. Now, if the specifications call for the volume of the box to be 1435, so 1,435 cubic inches. Okay, that's the specifications. That's what the volume of the box needs to be. Find the dimensions of the original piece of metal. So in other words, so we had that rectangular piece of metal, right? So we want to, using this information, find what does the dimensions of that original piece of metal that is fabricated need to be. So again, we're going to go through the steps of problem solving. So one, make sure you read the problem and know what the goal is. Here we want to find the dimensions of the original sheet of metal, right? And then we're going to use the information that's given to us. Well, what do we know, right? So we got to assign the variable. And so what are we trying to look for? We're trying to find the dimensions of the rectangle. Well, what are the dimensions of the rectangle? Well, we have length and width. That's true, but we also know the length of the square piece, right? We don't know the length of the square piece of that's being cut out, okay? But we also know that the length is 3 times the width. So let width be represented by x. Now we could use w too, okay? So let x be the width in inches, and so then now the length is 3 times the width, which is x. Okay, so now we can do that. Okay, so now we can have a way of representing the length and the width of the two dimensions of the original piece of sheet metal. Right? Okay, so now the box is formed by cutting 5 plus 5, 10 inches from both the length and the width. Well, how did we get that? Because it says equal-sized squares measuring 5 inches on a side. That's the key. Okay, so that means a box is formed by cutting 5 plus 5, 10 inches from both the length and the width. Why is that? Because if you draw, okay, here's where drawing a picture is very helpful, right? So here's our square, and what are we going to do? We're going to cut a square here. We're going to cut a square here. Oops. We're going to cut a square here. And we're going to cut a square here. And we know that this is 5 and this is 5 for all of them. And so what does that mean? Well, we're going to cut 5 at this end of this side, right? So that means this is 5, right? This is 5, right? And so this is 5, 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 this is 5. So we're going to have 5 cut from this side, 5 cut from this side, so there's 10 here. And we're going to have 5 cut from this side and 5 cut from this side, so there's 10 there. So we're going to have 10 inches cut from all of the different sides. That's what they mean, from the length and from the width. So that's where that 10 inches comes from. Okay, so the length of this side here is what? X. Right? So that's going to be the length from here to here. And the width is going to be what? 3x. Okay? And so this is the idea. So if you drew a picture, this would be perfect because this tells you everything you need to know, because this is the flap that's going to fold it up. These are the 4 flaps. Okay, once you cut out each of these corners. Okay? So now, what else can we do? Okay? This is what we're going to do. Okay? So let me erase. Oops, hold on. Oh, where is it? Let's erase. There we go. Okay, so this is what we have. Okay, I like your picture a lot better. Okay, so here's what we have. So now this side is 3x, so that means this flap is going to be 3x minus 10. And then this flap here has to be x minus 10, right? Because we're subtracting 10 from both sides, right? So the dimensions of the box has to be what? Because these flaps that are going to create the box has to be 3x plus 10, x plus 10, and then the height, because the height is the amount that we're cutting out. So we know the height of this box is going to be 5 inches. So there's where the 5 comes in. And so now we're going to solve. Okay, so now what we're going to do is we're going to write an equation. And the formula for the volume of a box is what? Length times width times height. So all we're going to do is just plug in what we determined each one to be. So the length was this, the width was this, and the height was this. So what does this have to equal? Remember, the volume has to equal the 1435 that we were given. So now here's our equation. So all we have to do is expand this out, and we're going to get a quadratic expression here. Okay? So note that the dimensions of the box must be positive numbers, right? So we must have positive values for these. Okay? So volume must be positive. Okay? So that implies that x must be bigger than 10/3, and, right, because if we solve these, right, if we solve this using the zero product principle, we have, so we actually don't have to expand this out. I'm sorry, I misspoke. So if we solve this for x, then x is equal to what? 10/3. Okay, but we can't be negative, so it's got to be, and 0 doesn't make sense, right? Okay, so x is equal to 10/3 here, x is equal to 10 here, and those are going to be our two values that we have to be bigger than. Okay. Okay, so just to reiterate, because we're solving for this one using the zero product principle, this is going to be x is equal to 10/3. This is going to be x equals 10. So that's when this thing is going to be equal to 0. Okay, so those are going to be the factors. But we know that since these have to be positive, x has to be bigger than 10/3 and bigger than 10. So that means x has to be bigger than 10 because both of them have to be true, okay? Because this can't be negative and this can't be negative. So they both have to be positive, and so greater than 10 will make them both positive. Okay, so this satisfies both of them, yeah, and I hope that makes sense. So x has to be bigger than 10. Now what we're going to do is we're going to solve this, right? So this came from this, right? So they expanded this out. And so we get this equation. So now what we're going to do is we're going to make this into the standard form. So we're just going to subtract 1435 from both sides, and we get this. Okay. So now we're going to solve for this one. And so we can simplify this because this is a common factor of 5. So we can divide everything by 5, and we can simplify the expression to this one. And now we can factor this. Okay. And so this is factorable, and this factors to 11x plus 11 times x minus 17. And so what do we get? We get either this is equal to 0 or this is equal to 0 using the zero product principle. And we get x is negative 11 thirds or x is 17. Well, we can't have a negative. So this one's automatically disqualified. And look, x equals 17. So this is good because x is bigger than 10. So we know this satisfies, so we know we have positive values for the dimensions, right? So the dimensions have to all be positive. So x equals 17 works. So only 17 satisfies this restriction that x must be bigger than 10. So thus, the dimensions of the original piece should be 17 inches by 51 inches by, or excuse me, I'm sorry, 17 inches by 51 inches. And of course, if we check, the length of the bottom box is 51 minus 2 times 5, which is 10, equals 41, right? And the width is 17 minus 10, which is 7, and the height is 5. And so the amount cut in each corner, right? So the volume of the box is what? Now we should get what? The amount that was specified, I think of the 1435, right? And lo and behold, 41 times 7 times 5 gives us 1435, which is what was required. And so it's good. So it works. Now, in this example here, we're going to use the Pythagorean theorem for right triangles. So recall that the Pythagorean theorem uses the relationship between one leg, the legs of the right triangle, and the hypotenuse, which is the line that connects, how do I explain this? The line across from the segment, the side of the triangle that's across from the right triangle, or the longest side of the right triangle. So what this says is if you have a right triangle, the sum of the squared lengths of the legs. So if you take this leg and square it and this leg and square it, if you sum those values, you're going to get the square of the hypotenuse. So a squared plus b squared equals c squared. Now in this case here, a piece of property has a shape of a right triangle. The longer leg is 20 meters, okay? 20 meters longer than twice the length of the shorter leg. Okay, so let me say that again. The longer leg is 20 meters longer than twice the length of the shorter leg. Okay, so now we've got a relationship there between the two legs. The hypotenuse is 10 meters longer than the length of the longer leg. Okay, so now we've got another relationship there that relates the longer leg with the hypotenuse. So the first one relates the longer leg to the shorter leg, and then the other one is the longer leg, relates the longer leg to the hypotenuse. Now we want to find the lengths of the sides of the triangular lot. Maybe it's a parking lot. Okay. So again, what are we finding? We're finding the lengths of the three sides of the right triangle, or in this case, the three sides of the lot, the triangular lot. So we're going to assign a variable. So what do we get? What's the unknown? Well, we're going to use some values here. So let the x be the shorter leg. Okay. So x is the shorter leg. And so 2 times, so the longer leg is 20 units more than twice the shorter leg, or yeah, the shorter leg. Well, if the shorter leg is x, then we're going to have 2x, and then we're going to add 20. And that's going to give us the length of the longer leg. Now, the hypotenuse, right? The length of the hypotenuse is what? That's going to be 10 units longer than the longer side, right? So in this case here, the longer side is 2x plus 20 plus 10, or 2x plus 30. So again, read the problems carefully. So we started with just choosing a variable for one of the legs. And in this case, we chose the shorter leg, x. So x represents the length of the shorter leg. The length of the longer leg is given by 2x plus 20. So then the length of the hypotenuse is 10 units longer than the length of the longer leg. So all we do is take the expression for the longer leg and add 10 to it. And so now we've got an expression for all three sides. And so now we can draw a picture. So we know the shorter leg is x, the longer leg is this, and the shorter leg is this. Okay? And so now we're going to write our equation, which is going to use the Pythagorean theorem. Okay? And now, what? We're going to, what? The hypotenuse is c. So substitute into the Pythagorean theorem, and then now we're going to solve. Okay, so notice, right, that we squared. So now we've squared this term. So again, just let's make sure we go back. So now we're squaring this one, and we're squaring this one, and that gives us this. Okay, so remember the middle term here and here. Okay. Now, this equals 0, standard form. So this is one of the two equations, right? Oh, hold on a second. Where? Oh, right. So here we're going to simplify this. Okay. So we're going to combine like terms, and we're going to simplify this expression. And so this is what we end up getting. We get x squared minus 40x minus 500. And so now this factors, and we get x minus 50 and x plus 10. And so now we know that either one of these is going to be 0 if we solve this. So that means x is going to be equal to 50 and x is equal to negative 10. Okay? Now, can the length of a triangle be negative? Of course not. No. And so distance has to be positive. If we're talking about the length of, we're talking about a piece of land, we're talking about the length. So it can't be negative. So x equals to negative 10 does not make sense. Okay. So the length of the sides has to be what? The length of the shorter leg is 50 meters. And then the length of the longer leg is 2 times 50 plus 20, which is 120 meters. And then the length of the hypotenuse is what? 100 plus 30 are 130 meters. Okay, so 50, 120, and 130. Now, the lengths are these. So now what we want to go back and see if it satisfies the words of the problem. Okay, and also satisfies the Pythagorean theorem. So does this squared plus this squared equal this squared? Now, air resistance. So now we're going to take the height of a projected object. So if air is neglected, again, so we're going to simplify things, and so there's no drag on this, on an object. Okay, so the height S in feet, so this is for position, S is for position, and of an object projected directly upward from an initial height of S sub 0 feet with an initial velocity of z naught or v naught, so S naught, v naught, or v sub 0, which is in feet per second for the velocity, is given by the equation this. So the height is given by negative 16 t squared plus the initial velocity times t plus the initial position or the initial height. Okay. So here t represents the number of seconds after the object is projected. The coefficient of t squared, negative 16, is a constant based on the gravitational force of the Earth. Okay, this constant varies on other surfaces such as the moon or other planets. Okay, so this negative 16 is a constant for Earth. Okay, and this actually is related to the gravitational constant. Okay. If a projectile is launched vertically upward from the ground with an initial velocity of 100 feet per second, neglecting air resistance, its height, s in feet above the ground, t seconds, is then given by what? This. Because we're talking about the ground, so the initial position is 0, right? So we get 0 here. And the initial velocity is what? 100 feet per second, so we get 100. So we get negative 16 t squared plus 100 t. So now after how many seconds will it be 50 meters above the ground? Okay, so now we're going to solve, right? So we're going to solve for t. So we must find the values of t where the height s is 50. So we plug in 50 here. And so now we've got a quadratic equation that we're going to solve for. So again, we're going to move the 50 over here. And we're going to solve for the quadratic equation, the standard form, right? And now what we're going to do is we're going to simplify this even further by dividing by 8, or excuse me, 2. So this becomes 8, 50, and 25. Okay? So now we're going to see if we can factor this. And it doesn't factor easily, and so we're going to use the quadratic formula. So now we plug in our A, B, and C, and then just carefully make sure you do it correctly and you use your calculator, and it reduces to this. Now when it comes to application type problems like this, we want to use our calculator because we want to get an approximate answer. And so we get 2 answers in this case, right? And the reason why we get 2 answers is because this is positive. So we're going to end up with 2 answers. So we get at t equals 0.55 seconds and t equals 5.7 seconds. So remember, the object goes straight up, and then it's going to stop, and it's going to come straight down. So it's going to reach 100 feet per second at the beginning, right, when it's shot up, and then it's going to slow down, and then it's going to come back down, and it's going to reach the same velocity at 5.7 seconds. Okay, and again, make sure you use your calculator so we can get the approximate answer. When it comes to application type problems, we don't want to normally leave it this way. we want to get an approximate answer. Okay. Now, so both solutions are acceptable since the projectile reaches 50 feet twice, once on its way up and then once on its way down. Now, how long will it take for the projectile to return to the ground? So, well, that's when the height is going to be 0, right? So we're asking ourselves, when is the height of the projectile equal to 0? Well, it's going to be equal to 0 when what? T is equal to 0, but we want the other value. So in this case here, we want to say, hey, when is the position 0? So in this case, obviously, if t is equal to 0, right, it's on the ground. So we don't care about that one. So we want to find, so what we want to do is factor out the t and then solve for the other factor. Right, so factor out negative 4t. And so in this case here, what do we get for this one? This one is irrelevant because we know it's going to be at ground level when at time equals 0 because it hasn't been projected yet. It hasn't been launched. Okay, so this is the one we want. And so here we want to solve for this one here, and we get t equals 6.25 seconds, and this is the one we want. Okay, so obviously it's on the ground when t equals 0, but they want to know how long before it returns to the ground. Well, that's going to be 6.25 seconds. And by the way, you could have gotten this by the answer from the other problem, because if you take this, 55.55 seconds. So it was after it was launched, so 0.55 seconds prior to that, it was on the ground. So if we add 0.55 seconds to this, that means it would probably, at this point, it was going to hit the ground in 0.55 seconds. And so if we add 0.55 seconds to this, what do we get? Do we get the same thing? I wonder. .55 seconds? And we do. We get the same answer, 6.25. Okay? Okay, the iRide trolley service carries passengers along the International Drive Resort area of Orlando, Florida. The bar graph shows iRide trolley ridership in millions. The quadratic equation is given by this. Y equals, where Y is what? Represents the number of the ridership in millions. Okay, and X represents the year. Okay, and so in this case, the number of years from 2000. Okay, so and this is only good from 2000 to 2013. So this models the data from 2000 to 2013. Okay, so now we're going to use this model that represents the relationship between ridership and year. It says use the model to determine ridership in 2011 and compare the result to the actual ridership figure of 2.1 million. Okay, so this is the actual ridership, 2.1 million. But we're going to use this model, this mathematical model, to estimate what it would be in 2011. So, and we'll see how close the estimate is to the actual results. Okay, so since x is 0, represents 2000, so x equal to 11 will be 2011. And so we're going to substitute in 11 wherever there's x. Okay, and so now all we have to do is use our calculator to find out what the ridership is going to be. And we get approximately 2 million. Okay, again, use your calculator. Now the prediction is about 0.1 million or 100,000 less than the actual figure of 2.1 million. Okay, so pretty close. 2.0 million, 2.1 million. Now, according to the model, in what year did the ridership reach 1.8 million? So now, this is in the millions, so we're going to use 1.8. So we're going to substitute 1.8 here for y. And now, in this case, we're going to solve for x. Now, here's, oh, this is a typo. This should be 1.8. So we're going to put 1.8 here. And now here's where we're going to have to use the calculator. Okay, we can't factor this, right? So we're going to use the quadratic formula. And this is going to be our A, this is B, and this is C. Okay? Or I'm sorry, I forgot. We got to put in standard form. So this becomes negative 0.16. Okay, so we subtract 1.8 from both sides. And we put it in standard form. Sorry, I meant to say that. So now we're going to put this in our calculator using the quadratic formula. So again, put this in your calculator and just plug and chug. And so we get two answers. We get x is approximately 2, or 2 million. And we get x is approximately 15.4 million. Okay, so now, so when will it reach 1.8 million in ridership? Well, according to this, we have 2, which would be what? X would be what? 2002. And then we also have X equal to 2015.4, right? About halfway past 2015. So this doesn't make any sense. Why is this wrong? Why can't we accept this? Because remember, this is only valid from 2000 to 2013. Okay, so 2002 corresponds to 2, x equal to 2. Okay, and then of course this one is more of a prediction. Okay, this outcome closely matches the bar graph and seems reasonable. Now the year 2015 corresponds to this one, but this is a prediction, right? Because it falls outside. Maybe I read the problem wrong. Did it once? It says, in what year did ridership reach 1.8 million? Yeah, so this would be the correct answer. So yes, I was right. Okay. Now, the year 2015 would be a prediction. So it predicts that ridership is going to be 1.8 million again in 2015. But again, the question was, when did the ridership reach a million? Not when will the ridership reach a million. Okay, and that is the end. So again, if you have any questions, reach out to me. Practice. If you have any, get stuck on anything, do some more of the examples in the textbook. Work on the suggested homework problems. And again, make sure you bring your questions ready to ask, or email me and I'll work help you through that, or I will bring it up in class and we'll work it out in class. So again, very important to make sure you're watching these videos. Keep up with the videos. That's the magic of the flipped classroom. You got to keep up with the videos, the lecture, and make sure you're doing the reading. Don't just watch the videos, but also read the textbook. Okay, that's very important. So when you come to class, you're going to be prepared to ready to engage the material, practice, and learn. Okay, until then, have a great day.